Right. We should be recording. All right, I'm going to share the screen. All right. Let's go to Brightspace. Go to 350. Go to content. All right. So I'm still grading your exams. Hopefully this week I'll be done. All right. Some of you may have a grade, but not all of them. All right. So I'm still working on that. So we are on the second third, as I said, of the semester. And usually the second third is where we focus on asymmetric encryption, right? So we're going to go over we've covered everything to do with symmetric encryption pretty much as far as we're going to take it this semester, right? So DES was the last algorithm that we covered. There's AES. You can study that one on your own for the term project at the end of the semester, for instance, and you can implement it if you'd like, as far as the algorithm. All right. So but we've covered symmetric encryption and block ciphers, basically, that confidentiality. That's still part of SSL. Right. And so we're going to continue to use these techniques, but we're not going to look at the algorithm so much anymore. We're not going to be using XOR so much anymore. And now, and we're going to focus mainly towards the end of the semester on libraries and just bringing everything together with PyCryptoDome or OpenSSL. All right. So now in this second third, though, I do have to cover asymmetric encryption. So now we're like switching gears towards that algorithm. So like I said, you know what asymmetric encryption is for. It's the one question that you've had since the beginning of the semester. How do I exchange the key securely? So a couple of things to remember. Asymmetric encryption is mainly used for the key exchange. Although you could encrypt a bigger message, it's not really designed for that. It's slower, right? So your Netflix movie would take 30 minutes to download versus a minute. You know what I mean? So you want to be efficient. So that's why we still use symmetric encryption, which is we've still discussed that it's pretty secure. So asymmetric encryption will mainly be used to encrypt a key, right? The symmetric key, basically, or the AES or DES key. So that's the idea. There are three methods that I mentioned that are available for asymmetric encryption, RSA being the most famous, the one that we're going to cover the most, but there's also elliptic curves, right? That's a more modern, newer thing. Blockchain and some cryptocurrencies do use elliptic curves, so they perceive it to be more secure. Okay, so we'll cover some of elliptic curve later in the semester. And then Diffie-Hellman is another mechanism for key exchange. But the main one that we're going to cover is RSA, right? So we're going to cover that today. Basically, I'll start with that. I gave a brief introduction of it on Thursday, just to kind of, in Python, get a sense for a very simple implementation. And then this week, we're going to look at a full implementation of RSA, and you'll see that it's actually an algorithm using several other algorithms to solve the task, right? But we're going to look at some of the principles of it. Obviously, I'm not going to do any proofs of RSA or anything like that. We're just going to go over we're going to look at the math as if it was like an algorithm, right? So we're going to think of it as, okay, these are the steps. And I've already alluded to some of these, like prime numbers and everything, and how interesting that can be, okay? So that's basically the plan. And remember, when we're using asymmetric encryption, we're using it or the public and private key to exchange the key, but we can also use it for authentication. So there's going to be that idea, right? So, and I do have some slides at some point that kind of summarize a lot of the ideas. So I'll get to those slides. But today we're just going to go over kind of like math problem type of thing and just solve by hand some of the concepts, and I'm going to start introducing certain things. So when I'm discussing the algorithm, I'll say something, it must meet this and other conditions, and then we're going to like GCD or whatever that is, and then we're going to have to like explore what GCD is, and there's a few other algorithms involved. Okay, so yeah, so this is RSA. I'll remind you, I gave you this link. So at this point, hopefully you guys I've started to read this like a blog post or an article or something about quantum computing and cryptography and how, it's the evolution, right, of cryptography, right? So there's some challenges to it if people can develop a good quantum computer, right? There's already algorithms to break things, cryptography such as Shor's algorithm, which is an algorithm written to be implemented on a quantum computer. At some point also in the semester, we will simulate a quantum computer with the Qiskit library in Python. So that basically is like we have a quantum computer. And I think it implements Shor's algorithm in there. So you'll see how with that, basically, we'll try to break RSA, right? And then there's another thing called FactorDB that can also help us. It's like a database, basically, of how to factorize numbers, okay? So that's basically the idea. All right, so here is, what we're doing this week. So this week, we're focusing on these documents. So we started these problems. We did problem 1, and I'll remind you, we went over those 2 functions, and those simple functions are the RSA functions. RSA is very much algebra, right? So if you liked algebra when you were in high school or in college, you'll like it. So it's very interesting. And then we did problems 1 and 2 in Python. And so this week we'll do problem 3 and problem 4, basically. Okay, and here, for the first time on problem 4, you'll be able to securely send a message, right? Because you'll also be able to securely exchange the key. So you can see here that this time you must exchange the symmetric key securely. So I've added that because you now have the tool to do this. Obviously, also, we're going to do OpenSSL of this later, and we're going to do PyCryptoDome of this as well. I'll remind you also that there will be a practical exam, right? A practical quiz or exam, whatever you want to call it. And that's going to happen around week 12, right? So usually what I do is we had exam 1 on week 6. So on week 12, we'll have the second written exam on the Tuesday. And then on the Thursday, we'll have the practical. I call it a scavenger hunt. So basically, I just hide a message, and I'm just going to encrypt it with like a whole bunch of all the techniques. So you have to then figure out how to break it. And
Is that within the span of 1 class period?
Yes, it's in class. That's a good question. So it's open notes. You can use whatever you want. Just it's individual work. Students always break it. So for many years, no one has, So some students have broken it in like under 10 minutes, and others take 2 hours, right? So it takes a while. So definitely you need to my point is keep track of all these scripts because I use all of them. And, everything, I'll use everything to encrypt. And I'll give you hints and things, but at the end of the day, you have to decrypt the message and, bring it up so I can see it. All right. So remember that's coming. Okay. So, we saw this document, which are the problems. Asymmetric encryption. You can see these are some of the slides. I'll cover these later probably. Here, you can see this py file. This would be the code for problems 3 and 4. So it's probably also on the GitHub, but you can download it from here. And we're gonna start modifying this code this week. And as I said, this is a full implementation of RSA. So you can learn like everything is implemented from scratch in this code. RSA continue. This is just another set of slides. This is probably, these are my notes. So basically what I'm going to do today is this. You can see that. So we're going to go over these problems. So this is what I'm going to discuss. Basically the algorithms. You have some notes there for your reference. So that's that one. And then this one, RSA steps. This is probably, the same thing. So these are my notes, basically, that I'm going to go over today as far as the algorithm. So we're going to do some problems. And you will have a problem this time around on the exam. There are some things that you can't easily calculate with a calculator. So I would have to give you that number because they're so big. right? But basically that's the plan. We're going to dig into these ideas. And then, as I said, please start reading the article on quantum and crypto. It's just, very relevant to what's going. All right, so now that we've talked about this, are there any questions about anything before we begin? All right, great. So we're gonna just start going over the algorithm. It's kind of the idea. So I will need the whiteboard for this. Right. So today we're going to start the discussion of RSA. Okay, so I'm going to go over RSA. Okay, so that's the okay. All right, so what is RSA, right? So RSA is a cryptographic algorithm which was developed by three people, Ron Rivas, Adi Shamir, and Leonard Edelman at MIT. Okay, so the algorithm is named after them, and it was developed in 1977. 1977. So they had this other technique by Diffie-Hellman, which are also these two people that proposed the idea. So you have to understand what the problem was, right, in the 70s. Think about it, right? Computers in the 70s. So this is the era of Bill Gates and that generation who were the people that were developing the OSs and everything. And so they were already trying to do cryptography, and the key problem was how do we exchange the key securely? So there was Diffie-Hellman who proposed something, then there was a call, and there was like the idea, the problem, there was like the math intuition, and then finally these three people came up with the algorithm RSA, which became the standard for asymmetric encryption for many years. Okay, and so that has been what has been used mostly for all this time. So the idea with RSA, as I've stated, is asymmetric encryption. So RSA uses a public and a private key, right? So that's the key. So we have a public and a private pair. Okay, so we have these two keys. So public and private. Okay. So, something like the message is encrypted with public key and it can only be decrypted with the private key. All right. And that basically allows you to achieve confidentiality. The other way around, we achieve what? If something is encrypted with a private key and it's decrypted with the corresponding public key, we have achieved
Integrity.
Not integrity. It can only be decrypted with that public key. It was encrypted with a private key, and there's only one in the world public key that can decrypt it. So that achieves the principle of no. Confidentiality is if you encrypt with what? With the public key, and then you decrypt it with a private key. Only one person can decrypt it, correct? So it's confidential. But in this case, you take the message, you encrypt it with the private key, and it's decrypted with a public key. Everyone can decrypt it, but only that public key can decrypt it. Therefore, that helps you to achieve, yes, authentication. So you probably, all this time, want to exaggerate, but in your life, you've thought, oh, authentication is just passwords, something like that. So it's an exaggerated case, but right. And no, actually, cryptography can help you to achieve authentication. And we'll see this exhaustively when we look at the digital certificates, which are, signing. So you guys have heard signatures, digital signatures, and then certificate authorities, right? So the thing that makes the internet work. So actually, we'll have a really nice, and during the applications part, one of the first applications will be to look at how HTTPS works, right? So we'll create a web server, we'll fake a web server, and we'll have a client, the browser. And we'll need to establish that communication securely, and that will be done through a certificate authority. So authentication will be very important there, right? So we need to understand SSL, HTTPS, how the websites work and everything. But right now, we need to start at the beginning, just the algorithm itself, okay? All right, so what are the steps for RSA? So that's the next thing that I'm going to do. So let me create a new slide here. Okay. All right, so we have so now the RSA and the steps for RSA. The steps. Okay, so the first step is step 1. Randomly and independently select two large prime numbers, P and Q, such that P is not equal to Q, right? So select two prime numbers. Two prime numbers. Okay, P and Q. P and Q, such that P not equal to Q. All right, so we're going to need to select these. So you know what prime numbers are, right? And so we just need to find them. We'll have a function a little later on Thursday that will help us to create prime numbers. And the key thing is we're just going to give it really a length that's really big. Right? So big prime. All right, that's step number 1. Then step number 2 is going to be to calculate n. Calculate n, which is the product of P times Q. Okay, this in fact is one of, public and private keys are made up of a tuple of 2 items. All right, so this is going to be both in the public key and the private key. All right, so we're going to see that. So let's create a new slide here. All right, so your public key should be equal to E, comma, n, where n is the value we just calculated. All right, so n, sometimes called the modulus. So it's the value that is P times Q. And then the private key is going to be D, comma, n. All right, later on in the semester also we'll use OpenSSL to create a public and private key, and we'll extract these parameters from the file. But for now, we're just going to compute them by hand. All right, so this is something that we had done before on Thursday. Now I'm going to continue to parts that we hadn't looked at in the algorithm. So step number 3. All right, so calculate. So step 2 was calculate n, which is the product of P and Q, which are the 2 prime numbers. Step 3 is calculate a function phi. So we're going to calculate phi. I'll sometimes say phi. So calculate phi. Okay. Right. So that's a new parameter. This is sometimes written as the Greek letter, which I believe this is the Greek letter phi. All right. So you'll see that in notation, etc. So phi is going to be the product of P minus 1 times Q minus 1. All right, so that's the next step in the algorithm. So you can see here, a lot of the times we calculate n, but in the programs and also in the certificates, the P and the Q are retained, especially in the private version of it. Obviously, you don't want to have that in the public version of it. If you had P and Q in the public key, everything is broken, right? So that's the whole point. The security depends on the fact that it's very easy to calculate n from P times Q, but it's very hard to find P and Q given n. So that's what you want. It's like the holy grail. Okay, so but the P and Q for convenience and ease of use will be available in the private key file that OpenSSL and other programs generate, and also in our code. All right, so that's important. Make a note of that. All right, so step 3 then was to calculate a function phi, which is the product of P minus 1 and Q minus 1. Then we're going to go to step 3. So step 3, or step 4, sorry. Step 4. All right, now we need to select an integer e. So you can see this e here, right? So select e given some conditions. So for now, just to keep it very simple, I'm going to constrain, the wording here, but we will expand on this as we start looking at additional functions and additional operations. All right, so select an integer e. So select e. Okay, such that it meets the condition 1, this is 1, less, so E is somewhere between 1 and B. All right, so for this to work out, like the math has to meet certain conditions. This is one of them. This is the phi that we calculated here, right? So the E exponent needs to be chosen to be between 1 and phi. Okay. And other constraints for now, so I'll say such that this and other conditions for now. There are conditions such as something called GCD. So we will look, you guys know what GCD is already, actually. So we will just do some exercises on what that is, and then I'll show you how to more robustly obtain the value. All right, sometimes the E is called the encryption exponent. Okay, so just keep in mind. And these two items now make up the public key. All right, got it? But because you're doing this whole algorithm, by following these steps, this procedure, you get both E and D, and then you have N, and then boom, you have your public and private key. And then already the equations also to encrypt and decrypt. All right, that's step 4. Then let's go to step 5. Step 5. Step 5. All right, step 5, calculate D. So remember, we have E, comma, N, which is the pub. And then the private is D, comma, N. Okay, so given this information, calculate D. Calculate D, which is the decryption exponent. And here we have basically an equation that we're going to follow. Okay, so I'm just going to say again, such that D times E mod, and mod here being the operator, right, that we've already seen, the percentage in Python, right? We saw this last Thursday. So D times E mod phi should equal, this is an equal sign, 1. Okay? So basically, we're going to need several algorithms as we calculate RSA, and this will require an algorithm, right? So that we do an exploration so that when we pick a D, that D needs to meet this equation here. Okay. And then once we have that, basically we've calculated D. That's kind of it. All right. So in essence, this is the way that you calculate RSA. Pretty simple. The code implementation, obviously, is a little bit more rigorous. All right. So we know that that's the public key, and this is the private key. So the public key is the combination of the modulus, so N and E, and the private key is the combination of N and D. All right, so now the idea is with these parameters, you have your public and private key, and now you can just go ahead and encrypt and decrypt. And that's it. It's crazy, right? That's it. And this works, and it's unbreakable, at least that we know of, for 20 years, and the whole internet works thanks to this. Or elliptic curves, or, which elliptic curves, actually, I will just hint at it right now. It's similar to this. You're still getting these E's and D's, except that you literally have an elliptic curve, like a geometrical curve in space, which is a function. And then so you pick a point on that curve, and then just through an algorithm, you iterate through this curve, and you find another point, and you start to use those points to calculate these parameters, public and private key. Do you guys see that? So that's literally what it is. But at the end of the day, you always end up with these combinations. Okay? All right. So now that we have this one, and then we'll do a problem by hand. The public key, so I've said that. So remember that so if we think in terms of Alice and Bob here, Alice wants to communicate with Bob, and she will make her public key available, but not her private key, right? So this one, everybody has. You can literally go on your Twitter and write it there, or you can go on your website, or however you want to do it, your GitHub, and that's your public key. Everyone has access to it. The one that you keep secret is this one, though. The private key should stay, in your laptop, in a lockdown file, so that no one can have access to it. And based on that, anyone can go to your website or your GitHub. They find this E and D, they encrypt some message, and they email it to you. And then they're like, hey, I just sent you a message. It's really important. It's encrypted. I used your public key on your GitHub. So then okay, great. That public key corresponds to my private key DN. So then I'm just going to use these and boom, decrypt the message, and you've got it. Do you guys see how simple that is? That's it. There's no mystery to it. Okay, and then after all of this, basically, we're just going to start to combine a lot of these things to create, these are still the primitives, right? And we still need to combine a lot of this to make ever more complex things like digital signatures, certificates, and so on, right? Which are just combinations of these ideas. All right, so now Bob wants to communicate with Alice. So he wants to send her a message M, like the secret key for AES. Bob knows the public key of Alice, which is N, E, N. Now Bob will encrypt the message M using Alice's public key. So this is where it's really important that you work with partners, because now you're going to have, you will generate your public and private key pair, and then someone else will generate their public and private key pair. I even recommend that you say John Smith public, John Smith private. so that you don't lose track of whose key you're using. And then you need to decide, okay, I need to send a message to so-and-so, so I need to grab their public key, and so that they can decrypt that with their corresponding private key. Okay. So in this case, Bob will want to communicate with Alice. He wants to send her a message M. So let's draw this problem out. Okay. Go over here. Problem. All right. So we have Bob and we have Alice, right? Bob and Alice. So they each have a pub and a private. So Alice goes and she uses her program or OpenSSL or whatever it is, PyCryptoDome, and she will generate her public and private key. You only need to do this once, right? If you think that the keys are secure, you don't have to reissue them. But each person now has a key, the keys. So now we're going to look at this idea. So Bob wants to communicate with Alice. So we're going to send a communication in that direction. I'm also going to change color here. All right. He wants to send a message. He wants to send her a message M. So Bob now has a message M. He wants to achieve confidentiality, right? So Bob knows the public key of Alice, right? So Bob knows the public key of Alice. So Bob will proceed to encrypt the message M using Alice's public key, okay? So that's the key idea. All right, so let's consider that. So how do we encrypt? We are going to look at the function for encryption, which is C equal M to the E, right? Mod, remember that's the mod operation, N. You see that? So what is Bob going to use? I'll change colors here. So Bob will need to grab Alice's E comma N, her public key, right? So these parameters, this E is that E, this N is that N. Do you guys agree? So Bob is sending a message to Alice. He needs to use Alice's public key. Why? Because then Alice will need to use that to decrypt it, because only those, these key pair, this pair of keys correspond to each other. So something encrypted with this can be decrypted with that, basically. All right, so once this is the equation then for encryption. Create a new slide here. All right, now Alice, Bob will send, of course, the message, right? So Bob sends the message. Alice. So Bob will send the message C, right? The cipher encrypted, and now Alice needs to receive it and decrypt it, right? So Alice receives the ciphertext C from Bob, and Alice will use her private key to decrypt the ciphertext to get the original message. So how do we do that? We're going to have M equal C to the D mod N. Do you guys see that? So now what do we use here? This is really important. We have Alice private key, right? So Alice's private key is equal to D comma N. Okay, so then the parameters that go here are at D and that N. Got it? And based on this idea, she can take the ciphertext and obtain the message. Any questions? Yes, sir. It's the P times Q. So that's good. Let's go back to the algorithm. All right. So let's go back to the steps. RSA, the steps, right? Select two prime numbers, P and Q, such that P is not equal to Q. We start there. Just pick three prime numbers right now. 17 and 19, for instance, right? Those are prime numbers probably. Obviously, those are too small, so they would easily be discovered. So you want to have something much longer, as we will see on Thursday. P times Q gives you N. That's the N in question, right? Yeah. So I need to go back. And we'll do a couple of problems to drive this more. All right, so now the decryption is this function. So as I said, M equals C to the D mod. So let's just say mod N, basically, okay? All right, so, and that should give back the message. So this would be the decrypted message, such as the secret key. All right, let's do a simple example, all right? And then we'll do like 2 or 3 problems just to kind of drive this idea a little bit more, and then we'll go from there, okay? But yeah, pretty straightforward, right? Now, this is the math of it, right? The problem is things like this part. Like easy in the math, a little bit more challenging in the implementation. So for this, we'll look at some algorithms that we have available to solve this problem. All right, so now, as I said, let's just do another problem. Maybe a little bit more. All right, so simple example of RSA encryption and decryption. So step 1, choose 2 random prime numbers. So P equal 5, Q equal 3. Okay, so that's step 1. Step 2, compute N. N is going to be P times Q, right? So in this case, this would be 15, right? 15. All right, the next one, compute phi. Step 3. Phi will be P minus 1 times Q minus 1. So this should be what? 5 minus 1 is 4. And 3 minus 1 is 2, right? 2. So then the value should be 8. Do you see that? It's basically that. Now, let's just take a simple example here. Step 4, we need to pick a value that meets something called the GCD condition, which we will look at in a while, and that is also between 1 and phi. So basically 1 and 8 in this case. So that's the E that we need to pick. So any of the numbers in there, 2 to 7. So the number that actually would meet the GCD condition for E is 3. And don't worry, we will look at how to calculate that in a second. But that's the idea. Okay, so I've picked an E. Then I need to pick step 5, D, such that it meets that equation that I wrote. So I need to select D, where it's D times E mod B equal 1. Okay, we will also look at this in a second, this operation. So in this case, E would be, what is E? 3. And mod, and phi is 8 equal 1. So we need to find a value that meets that condition. Do you guys see that? So this is the second operation we need to look at. As it turns, yeah, so yeah, all right. So then all right, so that's kind of the first introduction to the algorithm. That's it. Not too bad, right? It's, at least the big picture of it is straightforward. Okay, so now let's just keep going deeper into it and into the different parts. Okay, so we're going to do a second problem. This one is going to be a little bit bigger numbers. And just so that you can see, and this is actually problem 2 that we did on Thursday in Python. So we've already solved this in Python. We're just going to do this. Okay, questions? All right, so let's do another problem here. Let's say problem 2. All right. So it says RSA encryption and decryption. So basically, let's start again. So step 1, calculate 2 prime numbers. So in this case, P is going to be 61. And Q is going to be 53. This already starts to get pretty big, right? We saw that in, okay, so now what do we need to do? We need to calculate N. That's going to be 61 times 53. So that should be equal to 3,233. Okay, so that's N. Then we need to calculate phi. That's going to be 60 times 52. And that should give you 3,120. Okay, so that's the first step. So now let's think of, like how I can give you problems on the exam, right? I might say, you now select E. Select E. All right. So, and then I'll give you, like multiple choice. So I'll say like, let's just do that. So 4,000. One, 17. All right. So we don't know everything, but based on what we know, which one of these is the best candidate for E? Which one do you pick? 17, right? And just because right now it's within the range, so it meets the condition. But also later on, there's other additional constraints that we need to check for it. All right. So, but yeah, good. So you can select 17. So then we're going to say that E is 17. Is 17. All right. So the next step is So to select D, I'm gonna need to well, actually I want to do it here. Stay here. So now we need to select D. I should have done it like this, sorry. So we select E to be 17. All right, and then final step, we want to select D. All right, and we know we have D times E mod phi. So how do we compute this, right? So this, you may have to compute this. So it's not so straightforward. So what I may again is give you 3 or 4 Ds, and then you just pick the one that meets the condition, right? So, but for now, we'll look at that operation in a second. So for now, this would mean that we don't know D, but we know E. In this case, it's 17 mod what is mod? What is phi? Phi is 3,120 equal to 1. Do you guys see that? And the number that should meet this condition is 2,753. Right? So when you do this operation, you should have that 1 basically equal to 1. All right, and that's basically it. So now you have all the parameters, so you can summarize. And I can give you all these parameters and then ask you for the public and the private key, so you should be able to write it out. I need to go to a new slide. So the pub given this problem would be E is 17, right? So 17, N was 3233. Oops. Right? And then the private key, D was 2753. And N should be 3233. Got it? So this is basically how it works. In the algorithm, in the private key, remember this is actually stored as the P and Q to, for the computation. Okay? All right, so now that we have, so this is your public and private key. Now I might give you a message to encrypt, right? So in this case, I'm going to say something like, all right, go ahead and encrypt. So assuming that the plain text message number is 65, so M equals 65. M equals 65, that's your plain text message. Calculate the cipher. So what is C? Okay, so what is C? So then, so you will need to write out the equations for the encryption and the decryption. So now let's do encryption. Well, the encryption will be what? M to the E, I should say cipher, C, M to the E mod N. So then cipher equals 65 to the 17. Starts to get big, right? Try calculating these things on a calculator. Just try. See what happens. All right, mod N. So N is 3233. All right. And then we have our C, so this should be equal to, this C comes out to, I think, 2790. The 2790. That's your cipher. So now we want to proceed to decrypt it. Okay, so obviously at this point, you send this over. You took you took Alice's public key, right? You encrypted it. You send it to Alice. Now Alice is going to use her private key. So this is all Alice, right? Let's say Alice. All right. So now we're going to do the decryption. So the decryption should be the M equals C to the D, correct? C to the D mod N, right? So that means if we write it out, M should be 2790 to the power of what? 2790 to the
2753.
2753. Yeah. So go ahead and try to punch that in your calculator right now. And these are like toy numbers, right? Toy numbers. Okay, so 2790. So that's why it's difficult to compute some of these things in a word exam, in a written exam, but we'll see. That's why I have to come up with like tricks on how to ask you the question, like multiple choice. All right, so 2790 to the 2753, and then we're gonna do mod what? Mod what?
3233.
Yep. So 3233, and then that should result in our M of 65. Now, luckily, I already gave you the code on Thursday that allows you to corroborate all these numbers easily, and you should be able to get them. But you know how to compute them with Python at least. And yeah, that's basically it. So these are the types of work problems that you can expect on the next exam or quiz. Just I have to get creative in how I ask the questions, but basically this is the process. So that's it. You just encrypted a message and so on. Obviously, as we move forward in the problems, there's real, technical things we have to deal with. So for instance, our key might be a sequence of hexadecimal values, right? As we have seen before, we know how to generate these secret keys with urandom and create the byte arrays, etc. So we will need to figure out, okay, how do I go about encrypting that, right? So that's something that we will look at on Thursday, basically, on how we can do that. And there's several ideas for that. We have done Python. Well, that's good. So there's several concepts that need to be addressed. One of them is GCD. Anyone remember what GCD stands for in math? Divisor, yeah. Greatest common divisor. But yeah, good one. So you all did this at some point, right? So you know what it is. It's just an operation. So the greatest common divisor is the largest positive integer that divides each of two integers, basically. Okay. So we'll do some examples of this, but that's one of the conditions that must be met. Okay. So we'll take a look at that. We'll need to define that. And then also the operation, this operation here, in the previous line. Yeah, this operation, right? So we need to know how to perform this operation just by hand. We'll look at it, although you know how to do this in math. So let's do that, actually. It'll be the same numbers, just to keep it consistent. So basically this one, right? I'm gonna do that. Okay. So take a look. So, so step 4 or 5, when we're trying to calculate D, right? Obviously think about this. So you have to like search for a whole bunch of D's, right? Until you find the one that meets the condition, right? So that is an algorithmic search that you have to do. But once you've found it, you can plug in the values and do the operation. So let's concentrate on that one. So the equation is D times E mod B or phi equal 1. Okay, so we're going to plug in the values now. We knew that D was what? 2753. E was 17 from the previous problem. E was 17. Mod phi was 3,120. And this is equal to 1. So then the operation, so this is just a multiplication. 2,753 times 17 should be what? 46,801, right? Yeah, if you try that, so it should be that. So 46,801 mod 3,120. So this is actually a division operation, right? So you probably remember that. And we just want the remainder of that to be 1. That's it. All right, so let's just go ahead and see how that should work. All right, so then we can do 46,801 divided by 3,120. You guys see that? So basically, this is what we need to proceed to do. So we're going to have 1, right? So 1 times 3,120, 3,120, and this should be equal to 1,560. Then you carry the 1, and then now you're going to say here that this is 5. So 5 times 3,120 is what? So 5 times 3,120 is equal to 15,600. And the difference between these two is 1. That's it. So that's the operation. So it seems like, it's pretty straightforward. All right. So this one then equals, so this operation here is this. So this is 1 equal 1. So that's a correct D that meets the condition for the RSA algorithm to work. Any questions? Yeah, so that's it basically. All right. So of course you wouldn't, I could just for fun give you a problem such as this, but in general, it's going to be done, through the program and through some algorithm because we have to find these basically. So those of you that like math, I can give you a special problem. All right. Okay, so we've gone over the logic. Let's see if I can find the other operation. Let's see. Oh, here it is. All right, so now we're going to look at how I just kind of like waved my hands and said, here, boom, 17, right? So we're going to focus in on that part and one of the additional constraints, which is the GCD condition, okay? It's just so that we have a better understanding of how the algorithm needs to do this search. All right, so we're going to do another problem. This one is even more in depth, okay, in the procedure. So let's create a new slide here. All right, so I think this is problem 3 if I keeping track of this problem. Three, right? All right, so problem 3, select 2 prime numbers. So P and Q. So here I'm going to select another set, 11 and 13, which should be prime numbers. Okay, we're going to calculate N. Which is P times Q. So that's going to be 11 times 13, which should be 143. Okay, then we're going to do phi. So step 3. And that, remember, is P minus 1 times Q minus 1. So that should be 10 times 12. And that is equal to 120. Okay. Right, so we've got these two. Step 4 was to select the E. So before I kind of made it, I skipped some parts. Now I'm just going to keep adding, steps. All right, so step 4, what is E? So now E will need to meet certain conditions that are, so we need to select E such that E is going to be, let's say just keep it between 3 and what is it? Phi, right? So that's 120. 120. But also that E, the rule is that what's the rule I'm looking at? So GCD, so we have to meet the GCD condition. GCD condition, so the greatest common divisor. So the GCD needs to be equal to 1, I believe. Let's see. Oh, here it is. Okay, so I'm here. I have the rule here now. So the GCD rule. Select E that has a GCD of 1 with phi. All right, so now you have this additional constraint for selecting E. It needs to be within this range, but also the E that you select has a GCD of 1 with phi. Got it? All right, so that's the operation that we need to take a look at now. And you guys can help me out to solve this problem. All right, so so how do we do it? We need to try some numbers, right? And select. So obviously this would require to look at a lot of numbers. I'm not going to do an exhaustive search because we would use an algorithm for this. I'm only going to do a few examples by hand. So let's try it. So I'm going to create a new page here. Okay, we're going to go there. So we've established that phi is 120, right? So we're looking for E, and we wanted an E that is within this range, but that the values also have a GCD of 1 with phi. Okay, so let's try one. So let's say I'm going to try, let's try 3. So I'm going to do it like, this is an iterative process, let's say. So I'm going to just try the first one. And I'm going to say that the candidate is 3. Okay, so if the candidate is 3, you guys help me out here. The greatest common divisor, GCD, between, oh, sorry, let me write this. Between 3 and 120, which is phi, is what? What is the greatest common divisor? It's the largest positive integer that divides each of 2 integers. So what's the greatest common divisor, the largest positive integer between 3 and 120?
3, because 120 divided by 3 is 40.
Okay, so 3?
Yep.
Okay, thank you, sir. So does this number meet the GCD condition? We established that the GCD condition says that it needs to equal 1. So maybe I need to write it as where GCD of E and B equal 1. Sorry, I ran out of it. Does that make sense? So we need to select E's that are within this range, but also that have that condition. Why? Because otherwise it's not secure. That's the whole point, right? So if you follow these rules, that everything will be secure, everything is going to work out. All right, so in this case, then it needs to be equal to 1. So if we go back to our script over here, we are looking for equal to 1. This does not meet that condition. Therefore, that's not E that we select. So let's try another one. Another candidate. So I'm going to do 5. E 5, comma 120. Again, what is the greatest common divisor between 5 and 120?
5, because 120 divided by 5 is 24.
Okay, 5. Great. Does this number, candidate 5, meet the GCD condition? No, because it's not equal to 1. You see, that's the logic. I'll do one more and we're done with this. So let's do 7. So GCD of 7, comma 120. What is that? Is this 1?
Yes.
1, right? So 1. Yes, exactly.
So the answer really is you need to pick a prime number most of the time.
Yeah. So, but it has to meet that condition. Yeah, but yeah, that's a good, yeah.
As long as the prime number is not a divisor, then it's one.
Yeah.
So, or
Also,
yeah, I like what's going on here. Good. But yeah, so that's the fun of this, right? That's the fun of how this works. So basically the algorithm says you pick that one. Do you guys get it? All right. So as I said, a lot of these steps have a little additional things to look at. This is one example of them, right? So it's not just picking this, but also considering this. And of course, this is now imagine if your prime numbers are really high, right? Right? So really big prime numbers. And then phi is going to be the multiplication of those two. So now the range is between something like 3 or 1 and a really large number. And you need to look through all of those, right? And meet the GCD condition. So it's an exhaustive search. And so we need an algorithm for that. And we will see that Thursday. Got it? Yeah, go ahead, please.
This might be a dumb question. I'm gonna forget. But can't you just divide phi by that first number, and if it's not equal to a whole number, it's fine?
Say that again.
Because I think you're just trying to make sure that that first prime number and phi, they aren't equal to each other. I mean, not equal. When you divide them, it doesn't give you anything. It has to equal 1, right?
It has to be equal to 1. So I'm just sticking by the rule here.
So there's no common factor.
Eric, yeah. So I'm just like literally, you can dig deeper into that for sure. But what I can tell you is you pick a number within that range that meets this condition. So maybe there are more than 1. That's possible.
So it's a range. It's not just the two numbers. Or I'm missing. I feel like I'm not missing.
You're picking a D within this range. So you just need to pick one.
Okay.
But that also, when you pick that value, that also the GCD between that number and 120 is equal to 1. So that's the algorithm. Yeah. All right. Like I said, dig deeper into these things, and see what you can find. Yeah, go ahead, please.
Can you only be one number, or is there like multiple?
There could be others. I mean, like, I don't know. I mean, it's possible. Think about all the RSA encryption in the world that has occurred and the numbers as vast as they are. Maybe so I will say this. So you're actually touching on something very interesting. We're picking E, right? Generally speaking, people actually just pick a specific E that's 65,000. So N is really important. E is actually a value that sometimes gets just like selected. So there's a condition like if the number is above certain pick like 5, let's say, and if it's greater than this, then you pick 65,000. So you'll see this, it's weird, but you do end up picking a number. I have it here actually. Because it's known that that number meets the condition, and really that number, what varies is the n. And that 65,000 and the n make up the public key. And they correspond to the private key, basically. So E sometimes is 65,537. Look into it, and you'll see it's true. So, but that's basically how it works. So it's going to be because think about it, it's a number between 1 and a certain number. That 65,000 it works. And given an n, and then the private key that was generated with that, the whole thing just works. We'll keep looking at this. You'll see the code on Thursday. But yeah, that's the general idea. Okay. All right. So we talked about this step. We've gone over a problem. We've gone over mod and what that operation is. Okay. All right, so we did this. So I guess we can finish this problem. Yeah, let's finish this problem, right? So this is the RSA example. So let's kind of go back to previous slide. Okay, so problem 3, we select 2 prime numbers, 11 and 13. N is 143, so 11 times 13. Phi is 10 times 12 equal 120. Then we were at step 4. So we want to select E within this range, less than phi, but also that it has this GCD equal to 1, right? So that's the process. So select E that has a GCD of 1 with phi. So we've done that for several candidates, and we've selected 7. So now the conclusion. So let's go over here. So we selected 7. So actually, I'm going to generate a new one. The limits. Okay. So it doesn't matter. I'll just start a new one. So we tried several GCD conditions for E, and we select, let's say here, I think it was step 4. We selected E equal to 7, right? So we selected that. That's a good one. It works. It will work. All right. So now that we have, so select E equals 7. Now we want to determine D. So step 5. So we find D. So we have that equation D E mod phi equal 1, right? So this condition then says E is 7. That's what we picked. Mod 120 equal 1. All right, so we have that there. So there is going to be a function for this. It's called the inverse function. It's referred to as the inverse function. You'll see that in the code on Thursday. That will allow us to find the D value based on this expression. So to find, so as I said, this requires an algorithm. So now we're going to define the name of that algorithm. So to find D, D, you will need to use something called the extended Euclidean algorithm, or EEA. To find D, we use EEEA, which stands for the extended Euclidean algorithm. This one will be in the code that I'll provide on Thursday, and it's written from scratch. So no libraries or anything like that. Like, you can literally debug it. All right. So basically, using EEA, we would use EEA, and you can think of it as a function, EEA, that would give us D. So in this case, D should be 103. Okay, 103. So now we can proceed to, this should meet the condition. So I'm going to go over here, new slide. So the equation would be 103 times 7, right? Times 7. Mod phi, which is 120. 120. And that should equal 1. Do you guys see that? Now you know how to compute this, right? So 103 times 7 is what? What is it?
721.
All right. Very good. All right. 721 mod 120, right? And equal 1. So we know how to do this now. We can check 721 divided by 120. So that is 6. 6 times 120 is 720. Got it? So it meets the condition of 1, and boom, that's basically, so it's like these checks almost, you can think of it that way, but you have found the D that makes this whole system work well. So given these parameters, we can easily then proceed to encrypt something. So in this case, to finish up this problem, if m equal 9, then to encrypt, we would do C 9 to the what? To the 7 mod n, right? What was n? 143. Thank you. 143. And this should give us a C equal to 48. So that's your encrypted cipher, basically, for RSA. Now we're going to decrypt it. So decrypt dot C to the D mod n. So this should be 48 to the 103 mod 143. Oops. Okay. And that gives us 9. And you can corroborate this with your Python code. just to make sure that it is. Okay. All right. So this was like the first introduction to RSA. We'll do a few more problems as we go forward, but hopefully you're starting to understand the different steps. And then there's things like the EEA algorithm, other algorithms that we can only really understand them algorithmically, right? So we have to look at the code or the pseudocode and start to visualize how that works. All right, so that is this is not homework, but just since you guys were like asking certain questions, so I will just kind of give you some thought, right? So something to try out at home. So normally the public key exponent E, will be 65,537. Okay, so we can say normally E is set to 65,537. That's a fun exercise, find some phi values, and calculate the GCD between 65,000 and that phi value. Okay, so just basically calculate GCD of 65,537 and some phi values. Remember that for us to use 65,000 as an E exponent, this would need to be equal to 1. Does that make sense, guys? So play with that idea. We will come back to that topic, but that's something for you to look at. Okay? All right, so I think it's a good stopping point right now. And then we will just continue the discussion of RSA in the upcoming classes. Remember, next Tuesday, what day is it? Tuesday, right? So next Tuesday is fall break, so no class. But we will have lab this week, and we will continue with the topics. Okay? All right. Well, we can stop here for today, and I'll see you guys.